Across the vast expanse of space, countless stars twinkle like celestial fireflies, each a radiant beacon in the cosmic tapestry. These distant suns, scattered across billions of light-years, have captivated humanity for millennia. Stars are colossal furnaces, powered by nuclear fusion, forging the very elements that make up our world and our very existence. Their life cycles, spanning billions of years, play a crucial role in shaping galaxies, seeding the cosmos with the building blocks of planets, and ultimately, life itself. The birth of a star is a breathtaking spectacle, a symphony of gravity, heat, and light that unfolds over eons. In this cosmic ballet, we witness the awe-inspiring power of nature and the intricate processes that govern the cosmos. Join me now as we embark on a journey to unravel the secrets of star formation, exploring the celestial nurseries where these luminous giants are born, and delving into the fascinating stages of a star's life, from its fiery birth to its eventual demise. Our journey begins in the vast, frigid realms of interstellar space, where enormous clouds of gas and dust drift silently through the cosmic void. These clouds, known as nebulae, are composed mostly of hydrogen and helium, the simplest and most abundant elements in the universe. Within these cold, dark clouds, gravity plays a subtle but persistent role. It gently pulls the gas and dust particles towards each other, causing the cloud to slowly contract under its own weight. As the cloud collapses, it fragments into smaller, denser clumps, each a potential site for star formation. As gravity draws the material inward, the cloud begins to rotate, slowly at first, then faster as it contracts further. This rotation helps to distribute the angular momentum of the collapsing cloud, preventing it from collapsing entirely under its own gravity. Over time, the density of the collapsing cloud increases, and the temperature at its core begins to rise. The stage is now set for the next phase in a star's birth, the ignition of nuclear fusion. As the core of the collapsing cloud continues to heat up, it reaches a critical temperature of about 10 million degrees Celsius. At this extreme temperature, a remarkable transformation occurs. Nuclear fusion ignites within the core. Hydrogen atoms fuse to form helium, releasing an enormous amount of energy. This fusion reaction is the engine that powers a star. The energy released from the core creates an outward pressure that balances the inward pull of gravity. The ignition of nuclear fusion marks the birth of a star, blazing with light and heat. With nuclear fusion ignited in its core, the star enters a long, stable period known as the main sequence. This is the longest stage in a star's life, and it is during this time that it shines most brightly and consistently. Our Sun, a typical main sequence star, has been in this phase for about 4.6 billion years and is expected to remain so for another 5 billion years. During the main sequence, a star's size, temperature, and luminosity are determined by its mass. More massive stars have stronger gravitational forces, which compress their cores and increase the rate of nuclear fusion. As a result, massive stars are hotter, brighter, and have shorter lifespans than their less massive counterparts. Throughout its main sequence lifetime, a star gradually converts hydrogen into helium in its core. The energy released by nuclear fusion continues to counteract the inward pull of gravity, maintaining the star's equilibrium. Eventually, the star will exhaust the hydrogen fuel in its core, and its life on the main sequence will come to an end. As a star nears the end of its life, it faces an energy crisis. The hydrogen fuel in its core, which has sustained it for billions of years, begins to run out. With less hydrogen to fuse, the outward pressure from nuclear fusion weakens, and gravity begins to gain the upper hand. The star's core contracts under the relentless pull of gravity, causing the temperature and pressure to soar. This triggers a new wave of nuclear reactions in the core and surrounding layers, fusing helium into heavier elements like carbon, oxygen, and even iron. These late-stage fusion reactions release even more energy, causing the star's outer layers to expand dramatically. The star swells to an enormous size, becoming a red giant or supergiant, depending on its initial mass. Low-mass stars, like our Sun, will eventually shed their outer layers into space, forming a beautiful expanding shell of gas called a planetary nebula. The core of the star, now a dense hot object called a white dwarf, will slowly cool and fade over billions of years. Massive stars, on the other hand, meet a more dramatic end, triggering a supernova explosion. The explosion blasts the star's outer layers into space, seeding the interstellar medium with heavy elements and leaving behind a neutron star or a black hole. Astronomers have developed powerful telescopes and instruments that allow us to observe star formation in action. By studying different wavelengths of light, including infrared and radio waves, we can peer through the dust and gas that often obscure these stellar nurseries. One famous example is the Orion Nebula, a vast star-forming region located about 1,350 light-years from Earth. This nebula is visible to the naked eye as a fuzzy patch in the constellation Orion and is a breathtaking sight through a telescope. Infrared observations of the Orion Nebula have revealed hundreds of young stars still embedded in their natal clouds of gas and dust. These protostars are still in the process of gathering material and contracting, their cores not yet hot enough to ignite nuclear fusion. Another spectacular example is the Eagle Nebula, famous for the pillars of creation, where new stars are being born. The birth and death of stars are essential processes in the grand cosmic cycle of matter and energy. Stars are the cosmic furnaces where lighter elements are fused into heavier ones, enriching the universe with the building blocks of planets, life, and everything we know. The iron in our blood, the calcium in our bones, and the oxygen we breathe were all forged in the cores of stars that lived and died billions of years ago. When we look up at the stars, we are gazing upon our own cosmic origins. The death of stars, while marking the end of one stellar story, also sets the stage for new beginnings. The material expelled in stellar explosions, enriched with heavy elements, eventually becomes part of new generations of stars and planets. Our own solar system is thought to have formed from the remnants of a previous generation of stars. The Sun, the Earth, and all the life we know are products of this cosmic recycling process, a testament to the interconnectedness of the universe. Thank you.